Section 19.1, Nomenclature and Classification of Enzymes. Enzymes are often classified by placing them in categories according to the reactions that they catalyze. So we're going to look at examples of these 6 types of enzymes and the reactions that they catalyze. Oxidoreductases are reactions that catalyze redox reactions, and you can kind of figure that out from the name. It has ox and read in it, so redox reactions from our oxidoreductases, and they can be further divided into 2 subclasses, reductases and oxidases. So if we take a look at this example reaction that's here, we have this molecule that we call lactate, and then we have this NAD+, which I told you before is a type of coenzyme, and we'll talk more about that later. But it says we have this enzyme here. So this is the enzyme, lactate dehydrogenase, and then I form this molecule pyruvate, and I get this other compound, NADH. So what's actually happening here? Well, you might remember that in organic chemistry, we talk about oxidation as being the loss of hydrogen atoms or the gain of oxygen atoms. And if you think about what's happening here in this reaction, not only am I losing hydrogen atoms when I go from lactate to pyruvate, but I'm also gaining bonds to oxygen. So this is an oxidation reaction. So hence, lactate dehydrogenase would be classified as an oxidoreductase. I should also point out that oxidation and reduction are complementary processes, meaning that you can't have oxidation without reduction, and you can't have reduction without oxidation. So again, you can see that the lactate is being oxidized to pyruvate, but also the NAD+ is taking on a hydrogen. And if we think about our definition of reduction, reduction is the loss of oxygen atoms or the gain of hydrogen atoms. So the NAD+ is being reduced. So therefore, our lactate dehydrogenase is an oxidoreductase. Transferases are enzymes that transfer a group from one molecule to another. For example, transaminases catalyze the transfer of an amino group. A transmethylase is pretty easy to figure out what that transfers. It transfers a methyl group. It's right in the name. Another one that's very important but not abundantly clear is a kinase. And a kinase transfers a phosphoryl group. So if we take a look at this kinase, hexokinase, what it does is it takes the molecule glucose and it transfers a phosphoryl group over here in this position. So the hexokinase, again, kinases are responsible for the transfer of the phosphoryl group. So here's my phosphoryl group highlighted in yellow. And this is actually the first reaction in glycolysis, and we will cover this reaction in chapter 21. Hydrolyses are enzymes that cleave bonds by adding water. Phosphatases remove phosphate groups from proteins. Peptidases hydrolyze peptide bonds. So they literally break apart amide bonds. Glycosidases, an example would be amylase. Those hydrolyze glycosidic bonds, so they'll break apart polysaccharides into monosaccharides. And then lipases hydrolyze ester bonds in triglycerides. So here's an example that shows lipase. So here's our enzyme, lipase, and it's hydrolyzing all of the ester bonds in this triglyceride. So I have 3 ester bonds, and you can see it's breaking all 3 of those bonds. And to do that, it's going to require 3 moles of water in order to break that down into glycerol and fatty acids. So hydrolyses are involved in breaking bonds. A lyase, whenever you see a catalytic reaction that involves a double bond, it's a clue that it involves a lyase. So lyases, they catalyze the removal of groups to form double bonds, or the reverse, they involve addition to double bonds, so breaking a double bond. And we could also have other kinds of lyases like decarboxylases, which involve the removal of a carboxyl group. So here's a carboxyl group, the group that's found on a carboxylic acid. In synthases, those catalyze synthetic processes. So if we take a look at this lyase, fumarase, so here's our enzyme, we have fumarate, and here's our double bond in the molecule. And what are we doing? We're catalyzing the addition or the breaking of that double bond, and we're adding water to it. So we're taking fumarate, which has a double bond, and we're converting it to malate. So in this case, we're breaking a double bond, and we're adding something to it. So fumarase is a lyase. Section 19.2 deals with the effect of enzymes on the activation energy of a reaction. So activation energy, we symbolize this as EA. And the way that an enzyme affects activation energy is that an enzyme speeds up a reaction by lowering the activation energy. So what we're going to do is we're going to see a decrease in activation energy in an enzyme catalyzed reaction. And the way that it does that is by changing the reaction pathway, which provides a lower energy route for conversion of substrate to product. Now recall that every chemical reaction is characterized by an equilibrium constant, K equilibrium. So if I have a simple reaction like the one that's shown over here, the equilibrium constant for this reaction is defined as the concentration of B to the power of the stoichiometric coefficient divided by the concentration of A to the power of its stoichiometric coefficient. So the equilibrium constant, K equilibrium, is actually a reflection of the difference in energy between the reactants and products. It's just a measure of the relative stabilities of reactants and products. No matter how the reaction occurs, the difference in energy between the reactants and products is always going to be the same. So for this reason, an enzyme can't alter the equilibrium constant for the reaction that it catalyzes. It can only provide a lower energy path for the conversion of the reactant to product, and in this way, it speeds up the reaction. So here are two diagrams of the energy difference between reactants and products, and we have the diagram shown for an uncatalyzed and a catalyzed reaction. Now notice that the difference in energy between the reactants or the substrate and the products, in both cases, it's the same. So the difference in energy here, this delta E, is the same in both of these cases. The same number, same difference in energy. What's changed is the activation energy. You can see in the uncatalyzed reaction, I have a very large activation energy, whereas in the catalyzed reaction, I have a much smaller activation energy, and this is how we increase the rate of reaction significantly. Section 19.3 deals with the effect of substrate concentration on enzyme catalyzed reactions. So the rates of uncatalyzed reactions increase as the substrate concentration increases. For example, the rates of an uncatalyzed chemical reaction will often double if you double the concentration of the substrate. Therefore, as long as the substrate concentration is going up, there's going to be a direct increase in the rate of reaction. But for enzyme catalyzed reactions, this isn't the case. Although the rate of reaction is initially responsive to the substrate concentration, at a certain concentration of substrate, the rate of reaction reaches a maximum value. And that's what's shown here. So you can see that in the uncatalyzed reaction, that as long as I'm increasing the concentration of the substrate, the rate of the reaction is going to increase, and it follows this linear slope. Now, initially, the enzyme catalyzed reaction follows the same trend. So if you were to follow this line, you would be able to trace it into a straight line like this. But what happens is that it drops off. So as the substrate concentration increases, the rate of reaction initially increases, but then it tapers off and it reaches that maximum value. So at that maximum value, the active sites of all the enzyme molecules are occupied. They're all filled up by substrate molecules. So the active site is the region of the enzyme that specifically binds the substrate and catalyzes the reaction. So a new molecule of substrate cannot bind to the enzyme molecule until the substrate molecule that's already held in the active site is converted to product and it is released. A new molecule of the substrate cannot bind to the enzyme molecule until the substrate molecule that's already held in the active site is converted to product and then is released. Based off of this information, we can figure out that the enzyme catalyzed reaction must occur in two stages. So the first stage is going to be the formation of an enzyme substrate complex. And the substrate is nothing more than the starting material or the reactant. So this is where the substrate binds to the active site of the enzyme. And this is a rapid step. So this is the fast step. Then when we convert the substrate into product and release the product from the enzyme, this step is the slow step. And this is what we call the rate limiting step because the rate of the reaction is actually limited or controlled by the speed which with the substrate is converted into the product and then released. So in the end, the reaction rate is dependent on the amount of enzyme that is available.